Have you ever just stopped, looked at a brick wall, and really thought about what it's truly made of? I mean, we know a wall is made of bricks, right? And those bricks are made of silicates. We also know that the human body is made up of organs, which are made of tissues, which are, built from microscopic cells. But what if we keep zooming in, past the cells, past the silicates? What do we eventually find? Are living, breathing beings like us and non-living things like a house ultimately built from the exact same microscopic building blocks? What is everything actually made up of? And are these absolute smallest units truly indivisible?
Welcome to today's Explainer. Today we are taking a fascinating journey inside the atom to uncover the hidden building blocks of reality. We're going to trace the steps of the brilliant scientists who boldly ventured into this invisible world to figure out what we're all actually made of. It's going to be a fun ride.
So here is our roadmap for solving this atomic mystery today. First, the quest for the atom. Then, cracking the atom open. After that, the nucleus and beyond. Next, we'll decipher the chemical alphabet. And finally, we'll map out the atomic blueprint. Let's dive right in.
Part 1. The Quest for the Atom. Ancient Mysteries to Dalton. Let's kick off our historical detective story by looking at the earliest philosophical thoughts on matter.
Our journey actually takes us back more than 2,000 years, right into the intellectual landscapes of ancient India and Greece. Around 500 BCE, the Indian philosopher Acharya Kanada suggested something pretty wild for the time. He said that if you divide matter, or dravya, over and over again, you eventually hit a wall. You reach a stage where the particles just can't be divided anymore. He called these infinitely small particles parmanos and recorded this idea in the Vaisesika Sutras. Now, right around that exact same time, Greek philosophers Leucippus and Democritus proposed a remarkably similar imaginary idea, calling their indivisible particles atomos. But it wasn't until way later, fast forward to 1808, that English scientist John Dalton proposed the very first scientific atomic theory based on actual experiments. He boldly declared that atoms are the fundamental, unbreakable building blocks of literally all matter.
Part 2. Cracking the atom open. The Thomson era. Dalton's theory was a great starting point, but you know how science is. The plot thickened.
In the late 19th century, scientists started discovering radioactivity, and they quickly realized this supposedly indestructible atom could actually be broken apart into even smaller pieces. Enter our first major scientific detective, J.J. Thomson. Back in 1897, Thomson was studying how electric currents conduct through gases at super low pressures. He used this cool glass cathode ray tube with a high-voltage power supply, and he saw these mysterious rays shooting from the negative cathode to the positive anode. By testing these rays, Thomson figured out something truly groundbreaking. They weren't just rays. They were streams of tiny, negatively charged particles with a mass way smaller than the atom itself. Boom! He had just discovered the electron, proving once and for all that atoms actually have subatomic components inside them.
But this raised a massive puzzle for Thomson. Atoms are naturally electrically neutral, right? So if they have these negative electrons running around inside them, where exactly is the positive charge to balance it out? Well, he came up with what became known as the plum pudding model. But honestly, a watermelon is a much better way to picture it. Think of the atom as a sphere of positively charged matter, like the red fleshy pulp of a watermelon. And the negatively charged electrons? They're just embedded throughout that red pulp, exactly like the black seeds. It was a really simple, elegant first attempt to explain how positive and negative charges stay perfectly balanced inside a single atom.
Part 3. The Nucleus and Beyond. Rutherford's Breakthrough. Now, science is all about testing ideas, and Thomson's neat little watermelon model was about to be completely shattered.
In 1911, Ernest Rutherford, along with his researchers Geiger and Marsden, set up the incredibly famous gold foil experiment. Here's what they did. They fired a narrow beam of tiny, positively charged alpha particles at an insanely thin sheet of gold foil. Now, based on Thomson's watermelon model, where the positive charge is all spread out like soft pulp, Rutherford totally expected those alpha particles to just punch straight through with basically no deflection. But the reality? Oh, it was shocking. While most particles did pass through, some sharply deflected off to the side, and incredibly, a few actually bounced straight back. Rutherford later said it was literally as surprising as firing a cannonball at a piece of tissue paper and having it bounce back and hit you. Just mind-blowing.
The staggering conclusion Rutherford drew from these bouncing particles totally ruled out the whole plum pudding idea. He realized the atom's positive charge and almost all of its mass are not spread out at all.
Instead, they're densely concentrated in this incredibly tiny central region that he called the nucleus. How tiny are we talking? Well, the nucleus is about 100,000 times smaller than the atom itself. To put that insane scale into perspective, if an atom were the size of a massive 100-meter cricket ground, that heavy, dense nucleus would be just a single tiny grain of black pepper sitting right on the center pitch. That means the vast majority of an atom, and therefore the vast majority of the solid matter you and I touch every single day, is actually just pure, empty space.
So Rutherford proposed a planetary model, basically suggesting that electrons orbit this central nucleus kind of like planets orbiting the sun. But this brought up a really massive physics problem. We know that any particle moving in a circular path is constantly accelerating, right? And a charged accelerating particle should continuously lose energy. So you gotta ask, if these electrons are losing energy as they zip around in circles, why don't they just spiral inward and crash directly into the positively charged nucleus? If Rutherford's model was entirely correct, atoms would just instantly collapse, and matter as we know it simply wouldn't exist.
Enter Danish physicist Niels Bohr. He solved this whole collapsing atom problem with an absolute stroke of genius. He proposed that electrons don't just move randomly, they're actually restricted to specific fixed circular paths. He called these stationary states, or energy shells, and labeled them K, L, M, and N, moving outward from the nucleus. The real game changer in Bohr's theory was his rule that as long as an electron stays in one of these allowed shells, it literally does not lose energy. An electron only changes energy when it actively jumps from one specific shell to another. And there it is. That beautifully explained exactly why atoms remain perfectly stable.
Okay, but scientists still had a lingering math problem. Take a helium atom, for example. It has 2 positive protons, but it somehow weighs 4 times as much as a hydrogen atom, which only has 1 proton. So where on earth was all that extra mass coming from? Well, in 1932, James Chadwick finally found the missing puzzle piece, the neutron. A neutron has roughly the exact same mass as a proton, but, and this is key, it carries absolutely 0 electrical charge. Neutrons just pack right into the nucleus alongside the protons. They provide that extra mass and actually help bind heavy nuclei together, preventing those positively charged protons from just pushing each other apart. So with electrons, protons, and neutrons, our subatomic roster was finally complete. Part 4. The chemical alphabet. Symbols of elements. Now that our investigation into the fundamental physical pieces is complete, let's shift into architect mode and see how we actually label these unique elements.
Back in the early 1800s, John Dalton actually tried inventing simple pictorial symbols for the elements, but as we kept discovering more and more of them, drawing all those little circles and dots got super impractical. Today, we rely on the IUPAC naming rules. The rules are pretty straightforward. An element symbol is just 1 or 2 letters. The first letter is always capitalized, and the second is strictly lowercase. So aluminum is a capital A and a lowercase l. And what's kind of fun is that a lot of these symbols are actually derived from their ancient Latin names. That's exactly why iron is Fe for ferrum, silver is Ag for argentum, and gold is Au for aurum. This whole system ensures that scientists all over the world can communicate flawlessly, no matter what language they speak.
Part 5. The Atomic Blueprint, Notation and Rules. Let's look at how we measure and map the specific ingredients of an atom to completely understand its chemical identity.
The absolute most crucial point here is the atomic number, which scientists call Z. This is simply the number of protons found in the nucleus of an atom. You can think of the atomic number as the ultimate unchangeable ID card for an element. If you have an atom with exactly 6 protons, it is always carbon, no exceptions. If you have 11 protons, it's always sodium. If you could somehow magically change the number of protons in that nucleus, you'd change the entire identity of the element. It's the defining feature of reality's building blocks.
Next up, we have the mass number, denoted by the letter A. This one is the total combined number of protons and neutrons, which are collectively called nucleons, living inside that dense central nucleus. Since we know those little buzzing electrons orbiting the outside weigh basically nothing in comparison, the mass number tells us something pretty amazing. Practically 100% of the physical weight of any atom is packed tightly into that tiny, microscopic pepper grain of a nucleus. Finally, let's see how nature actually builds an atom from the inside out, using something called the electronic configuration. Those electrons we talked about, they organize themselves following a strict mathematical rule called the 2n² rule, where n is just the shell number. So the innermost K shell is shell number 1. Run the math. 2 times 1 squared means it holds a maximum of exactly 2 electrons. The next shell out, the L shell, is shell 2. So 2 times 2 squared equals a maximum of 8 electrons. Nature acts like a super meticulous bricklayer here. It always completely fills the inner shells closest to the nucleus first before cautiously moving outward to start filling the next energy level.
And that, my friends, brings us to the end of our journey inside the atom. Think about it. What started as just an abstract philosophical thought experiment thousands of years ago evolved into this relentless scientific pursuit that completely transformed human history. Understanding this microscopic architecture, knowing all about the nucleus, the energy shells, and those uncharged neutrons has allowed us to do absolutely incredible things. It gave us the tools to use isotopes to date ancient fossils and unlock the history of our Earth. It sparked the atomic age by showing us how to split uranium and harness monumental amounts of nuclear energy. So, as we continue to probe even deeper into this subatomic world, we really have to wonder, what new hidden secrets are still waiting in the dark, empty spaces of the atom? And how will they shape our collective future? Thanks so much for joining me on today's Explainer. Keep asking those big questions, and I'll catch you next time.